Back to our main example, the density function, and once again you can write it down if you haven't written it down yet. This function right here, f of xy equals x cubed plus xy squared plus 3y minus 10x plus 250. We're going to be considering optimizing this function over different domains. And our domains are going to be taken to be bounded sets that often also happen to be what's called closed. And I'll talk about more what that means in a few minutes. In the Mathematica code that we use today, it's going to be more convenient for us to enter the functions using curly braces for the input. That's going to end up being more convenient because I'm going to evaluate the function at points treated as lists in Mathematica. So it's going to be more advantageous for us to enter it like this. The first domain we're going to consider is this domain right here. I'm calling it D1. And oftentimes in this class when we're talking about domains, I'm going to use a cursive D. D1 because it's going to be the first domain we're going to consider. This is called set builder notation. I don't know that I've talked about that much in class before. But what you want to do is when you read this, the curly braces are not curly braces as in Mathematica. It's whenever you see something like this in math, it typically means you're dealing with sets or collections of things. This is the set of all points, x, y, and the assumed coordinate system would be rectangular coordinates in the plane, satisfying the property that x is between -5 and 5, and so is y. And note that these inequalities are less than or equal to's, not strict less thans, and that's actually going to be important. That is the domain we've been thinking about already, and we made the contour plot of that and made guesses about where the maxima and minima are. Let me review some other things. Here is the way you can get Mathematica to calculate the first derivative of this function for you with respect to x. The capital D means differentiate whatever's inside here, comma, whatever the variable you want to differentiate with respect to is. In this case x, in this case y. If I use the curly braces in this definition for f, I need to have curly braces in here as well. If you don't use the curly braces for the definition of f, then you would not use the curly braces inside the D operator either. All right, so that's going to produce those derivatives, and then I can go ahead and enter those functions here. Here's the first derivative and the second derivative, or excuse me, that's the derivative with respect to x. The derivative with respect to y is 3 plus 2x times y. That can be entered too. What about second derivatives? I think I might have shown you this once, but I'll show it to you again. You just have to reapply capital D. For example, if I want the second derivative with respect to x twice, there's how you do it. If I want the second derivative with respect to y twice, do it this way. So we're iterating D essentially. We're applying it twice. This inner thing from here to here, that's differentiating f with respect to x. And then you're putting that inside D as well and differentiating that with respect to x. That's going to be the second derivative with respect to x twice. And then you can also do the mixed partial. I can type x comma y. If I differentiate it with respect to x first, then y second, or I can do it the other way around and those should be equal. Those are always going to be equal for our nice functions that we deal with in this class. So we've got the fxx, excuse me, is 6x. fyy, the second partial with respect to y twice, that's 2x, and you should check these in your mind too. fxx is going to be the derivative of this with respect to x, 6x. Fyy will be the derivative of this one with respect to y. Treat the x as a constant, and you get 2x. This one is a mixed partial. Differentiate this one with respect to y and get 2y. You get the same thing if you differentiate this one with respect to x. The y is a constant, you get 2y. Again, Clause's theorem guarantees those will be the same when your function is sufficiently nice. All right, and you had in your completion homework, you had some problems where you had to use this based on something called the discriminant. It was the second partial with respect to x twice times the second partial with respect to y twice minus the mixed partial, second partial squared. This is called the discriminant, but it actually can be called a determinant of another matrix. This is not a matrix that comes up from cross products or anything. If you make a matrix whose a 2 by 2 matrix whose upper left entry is fxx, whose upper right entry is fxy, whose lower left entry is fyx, and whose lower right entry is fyy, the determinant of that matrix by Clause's theorem is going to be the same as this discriminant. So they could have called it a determinant. They sound very similar, but they decided to call it a discriminant. What does it equal in this example? Multiply these things, you're going to get 12x squared, fxx times fyy. Square this thing, you get minus 4y squared. That's a function of x and y. What do you need to do with this? What was the goal in using this for the completion assignment?
Find what a critical point is.
Well, once you know the critical points by setting the first derivatives equal to 0, which I have right here, and we solve this for x and y, we got 4 critical points, then do what?
Then find if it's a min or a max and stuff.
Yeah, you got to classify the critical points, plug them into this discriminant. If you got a negative discriminant, what did that tell you? There was a saddle point. So if d is negative, add a critical point. I'm talking about evaluating this function at critical points, and we had 4 of them for this function. The critical point is a saddle point. That's what happens when d is 0. So again, if you graph the surface graph in 3 dimensions and you sit on the saddle point, it's like you can sit in such a way that your legs go over the saddle. The shape of the graph, another way to think of it is it looks sort of like a Pringles chip. The shape of the graph in higher dimensions looks like that. That's what it looks like at a saddle point. So that's what's going to happen if d is less than 0. If d is greater than 0, then 2 different things can happen based on, the book takes it to be this thing, positive or negative. What happens if that second partial fxx is positive? What does that mean? Then the critical point is what? Say it louder. Local min. It is a local min. Back in calculus 1, the second derivative being positive meant your graph was concave up, which is intuitively why the point was a local min. But we've got more than one direction we can be concave up here. What about fyy? Why don't we have to make an assumption about that? Anybody want to hazard a guess? You might have wondered, I hope you wondered about it. You know, it's concave up in one direction but not the other. Well, you don't need to. Go ahead.
If they were opposite, then the d would have been, or then it would have been a saddle point, right? So if it's not a saddle point.
If d is negative, it's a saddle point. If d is positive,
yeah,
you can get a local max or a local min. Why don't we also need to assume fyy is positive?
Because then they're the same direction. Or the
Yeah.
same.
This assumption and this assumption together mean that fyy is automatically positive.
Yeah.
think about it here. If this is positive, d being positive is equivalent to this difference being positive, which means fxx times fyy is greater than fxy squared, which is positive. If you also assume fxx is positive, and you know this product is positive, that's got to mean fyy is also positive. So you are concave up in both directions. And that ultimately means in all directions, really. You're going to have a bowl shape and you're going to have a local min. But it is local. It's not necessarily the lowest point on the entire graph. It's just a local min nearby. That's the lowest point. On the other hand, if d is positive and that second derivative is negative, then it's like your graph is like a mountaintop. It's concave down. Then the critical point is a local max. It's the location of a local min and a local max. If I ask for local min and local max values, then you have to plug those points into the function to determine whether what the local max and min values are. Yeah?
Could you say the same if d is greater than 0 and fyy is greater than 0? Then you could assume fxx is greater
Yeah.
than 0 if you
Yep.
know either one.
It's symmetric, yep. This equation here is symmetric in these two things. If you switch them around, you get the same thing. If d is 0, then lots of different things can happen. That's kind of a degenerate case. And if d is positive and fxx is 0, I believe that's also kind of a degenerate case. Different strange kinds of things can happen. In fact, there's even something that's called a monkey saddle that can occur in strange cases where it's like a monkey is sitting on the saddle. The monkey can put its legs over the saddle, and also its tail can go back down where the function is increasing. It's called a monkey saddle. Strange kinds of things can happen like that. They don't typically happen, but they can happen. All right, we did solve for the critical points before. The exact formula for them was kind of messy, so we were satisfied with getting approximations with nsolve, these 4 points. Let me go ahead and show you a trick to figure out the function values of these points. Actually, let me go ahead and define a list. I'll call it crit points. That is going to be a list of these points. Negative 4.9, negative 0.493, I'll round them to 3 decimal places. Negative 0.493, comma 3.045. Positive 0.493, comma negative 3.045. 1.758, comma negative 0.853. And then negative 1.758, comma positive 0.853. All right, so that's a list of the critical points. I'll go ahead and plot them, and then I'm going to show you kind of a neat trick here. Let's see, where's my plot? Where's my contour map? I think I had it down here. I think I'll go ahead and enter the gradient vector as well up there. I'll copy and paste this up here. Enter that. That'll be handy. The contour map is down here, it looks like. I am not going to bother with an animation of anything. Let me copy and paste the show and the contour plot of this up here. And let's also use list plot to plot the points. Since I've given this list a name, crit points, I can just type in crit points here. Make them big, black say. Oh, where'd my contour plot go? Did I enter the function? Oh, I know why. It's because I forgot about the curvy braces here now. There we go. There's our 4 critical points. It'd be good to put the axes in here too, and maybe even get rid of them. No, I probably should keep the frame, but let's stick the axes in there. Okay, so you can see the axes. It might be a little dim on the video. Hopefully, you can see that there's the x-axis here. Here's the y-axis. The origin's right there. And if you look it over, you can see that those points seem about right. I'm going to show you a little trick now, kind of a fun trick that can evaluate the values of a function at all the points in some list. This is a list of points. I'd like to evaluate f at all these critical points to see the outputs. By the way, I should be able to guess what kind of outputs I'm going to get if you move the cursor over here. These level curves, you see outputs that are typically in the 240, 250, 260 range. So when I apply the function to these points, I should get outputs in that kind of range. The key to doing that is to using something called map. Map takes a function, in this case the function f, and applies it over whatever list you put next after the comma. And the list I'm going to put is critical points there. This list that I've defined. There we go. There's the outputs of the function at those 4 points. I can do it in one line of code. That. Let's see, which ones were the saddle points? These two are the saddle points. And the outputs for those 2 points are 259 and 241 approximately. This one was the one on the lower right. That was that darker or lighter? I forgot. I think it was darker. I think that one's a local min. Yeah, that's fairly low. And this one was in the upper left. That was a local max. That's fairly high. Let's get the use the discriminant test here, the second derivative test involving the discriminant. I can't just use a capital D in Mathematica because that's reserved for derivative. How about I call it discrim? It's fxx times fyy. I could have used subscripts, by the way, for the xx and the yy, but I'm just trying to save time without using subscripts. fxy squared. I can apply that over these critical points as well. I can do map discrim. Once I've defined discrim over the critical points, what should we see? Remember, the first two were the saddle. This was the local min, this was the local max. We'll get negative discriminant values there and positive discriminant values for the last 2 points. Yep, 2 negatives and 2 positives. So that confirms the first 2 points are saddle points, like I said. And the second 2 points are probably either local maxes or local mins, but we need to also apply fxx over the critical points. Although the only ones we care about are the last 2. We don't care about the sign of fxx at the saddle points. Didn't I define fxx? I think so. Oh, again, foiled by the lack of curly braces. Let's just put them here just for the purposes of getting that to work. Although then the script probably gets messed up. I'll try to fix this up before I put it on Moodle so it all works nicely. There we go. All we care about are the last 2, the fact that this one's positive and this one's negative. This one corresponding to the lower right point. That was, again, the min. Yeah, that's telling you the graph's concave up. This one's negative, corresponding to the upper left point. It's negative, telling you the graph is concave down. That one was a max. But those are only local maxes and local mins. The graph does seem to go lower. For sure, it goes higher and lower. Up here, you can see it getting close to perhaps 400 as I go up here. See values around 360 there. Down here, it gets down in the 100s and probably lower as I keep going down toward that lower left corner. So the global max and min are not going to occur at these critical points. But it will exist. There's a theorem in your book, and let me point it out. I'm not going to write it on the board. It'll take too much time here. It's a very important theorem, often called the extreme value theorem. Our book labels it existence and location of global extrema, global maxes and mins. It's on page 838. take a look at it. If you don't have your book, it would be good to look over somebody's shoulder or look at their book next to you here. Page 838. It says, first of all, assume your function is continuous. All right? No problem here. That function is definitely continuous. Practically all the functions we deal with are continuous, except when we're dividing by 0. No problem here, that's continuous. And suppose your domain is closed and bounded. Bounded means the domain doesn't go off to infinity in any direction. Okay? You can contain it in some disk centered at the origin. Definitely this square centered at the origin that intersects the axes at plus or minus 5. Definitely that's a bounded set. You can put it in any disk like this, that at least bigger than the distance here between the origin and this point, which would be what, square root of 50. It's bounded. It doesn't go off to infinity in any direction. Is it closed? What does closed mean? Well, closed sets can actually be pretty complicated, but for all the domains we deal with, think of it intuitively. A closed set is a set that contains its boundary, where essentially the boundary is the edge of the set, separating it from its complement out here, which would technically be what's called an open set, but I'm not going to get into that either. Okay, so for the domains we consider that are simple enough to draw in this kind of way, or maybe in some sort of blobby way like this, maybe with some holes in them, it's sufficient to take an intuitive understanding of being closed to saying, okay, this edge of the set, this boundary, is part of the set. That's what it means to be closed. If I did not include the boundary, which I would draw like this, or even if I included just part of the boundary but not other parts, that would no longer be a closed set. It would not contain all its boundary points. As far as the description of the set goes with the set builder notation, the important feature here, I can remember where I put it. There we go. The important feature here are that these inequalities are less than or equal to's. If I had made them strict less thans, that would tell me the boundary is not part of the set, and it would not be a closed set. Okay, so with this intuitive approach, with domains we can draw in this kind of way, if the boundary is in the set, if all boundary points are part of the set, then it's called a closed set. And in that situation, you can say two things. First thing it says is that f is going to have a global max and min value. There will be points in the domain where the output of the function at those points is as high and as small as possible. And no other outputs get bigger or smaller. And secondly, it also says those extreme values, the global max and global min, occur either at critical points in the interior of the set, the part of the set that's not the boundary, the shaded part here, or they occur along the boundary. So these four critical points in the interior of the square are the four possible candidates for where global maxes and mins could occur. Now this function, and this is not what's going on with this function, the global max and global min are going to occur along the boundary, probably either the upper left or lower left corner for the global mins, and either the upper right or lower right corner for the global maxes. However, you can imagine, it might be hard to come up with a formula for this, but if you sort of grabbed the peak, remember the graph is in front of the screen here, and pulled it, so to speak, stretched it to be really high. I don't know how you do that with a formula, but if you imagine doing that geometrically, you could make the output of the function at that point higher than the outputs along the boundary, in particular at these 2 points here. Theoretically speaking, that could happen. So definitely the global max and global min can occur at critical points in the interior. But in this case, it seems like they're probably going to occur definitely going to occur along the boundary. But how do you figure out where they occur? You had a problem or two like this, I think. You remember what you did? I'm suggesting what you should do here by going over this drawing. you should think about the function along each of these line segments, because that's the boundary. This line segment is where x equals 5. This one's where x equals -5. Up here, this line segment is where y equals 5. This one's where y equals -5. If you plug, for example, x equals 5 into the two variable function, you get a function of just one variable, y. That can be graphed normally. We've done that already. What is the function f of 5 comma y? It's this quadratic. And we can plot that over the domain, the closed interval from -5 to 5. Plot f of 5 comma y, where y goes between -5 and 5. It's going to be a parabola opening upward, and it looks to be highest at y equals 5. So along the right side of this square, the function is optimized, global max right there. The value is going to be around 460 something, it looks like. It's got a min there, which we could find by differentiating this function with respect to y. Do it in my head here. 3 plus 10y is the derivative. Set that equal to 0. We'll get what y is -3/10, -0.3. About there is where the vertex is. That's going to be a local min at least. Is it the global min for the function? The global min for the function 330 or 325 or so? No. That's going to be the global min along this boundary, but not overall the entire square. That's going to probably occur down here or up there. Let's plot some other functions. Actually, we can have more fun with this and put it in and manipulate. We did this before too. Make plots where x is your animation parameter going from -5 to 5. It's really the extremes -5 and 5 that we're concerned about, though, because that's going to correspond to the left and right boundaries. So when x is -5, this is the graph, and it looks like the graph is lowest over here, and output around 35 or so. That's corresponding to thinking about the function along this boundary here, and we're seeing that the output seems to be smallest down there. As we let x go up to 5, you can, you do see pictures of what the graph looks like for these intermediate values of x. However, all we care about is when x gets back to +5, or we get the graph we were just looking at a minute ago. What about the upper and lower boundaries? Just switch around the roles of x and y. Make x the thing you're plotting the function with respect to, and make y the animation parameter. Now the graphs are different. They look like cubics instead of quadratics, and in fact that is the case. For example, f of x comma -5 is this cubic there. When y is -5, this is the graph. That means that's what the outputs of the function are doing along the lower boundary. Y is -5 and x is going from -5 to +5. There we have a min and we have a max over there, though that max over there on the right is not as high as the max up here. We let y change so that we consider different horizontal lines. The graph changes, but all we care about is when y gets back up to +5. The graph looks very similar. In fact, it's just a vertical translation of the previous one. Plus 265 instead of 235. Based on this analysis, the global max value is going to occur right there, and the global min value is going to occur right there. The global min value I guess was 35. I think I remember that from the previous class. F of -5, I think is 35. Yep. That's the lowest output of the function. F of 5 is going to be the highest, and that's 400 something, close to 500, 465. On this domain, that's the highest possible value the function can have, and it does attain that value at that point. This is the lowest possible value the function can have, and it does attain that value at this point. The fact that the domain is closed is necessary. If I had used an open domain, like this, where the boundary is not included at all, then neither the global max nor the global min would exist. Seems a little strange. Wouldn't you say the global max and min are still 35 and 465? No, because the function never gets there. Since the boundary is not part of the set, it's not part of the domain, you can't consider the corners. They're not part of the domain. The function does equal 465 up at this corner, but you can never reach that if you stay in this domain. You can get arbitrarily close to it, but you'll never attain it. Likewise, you'll never attain 35 for an output function. It can get arbitrarily close to 35 and 465, but it never actually reaches it on this domain. But it does on this domain. So it's a subtle thing, but technically speaking, as the theorem stated, it is necessary. Another thing that can happen when your domain is open, just consider a one-variable example, is your function could have a vertical asymptote and not have a greatest value that way. Okay, all positive values past a certain point are possible here. There is no highest value. Don't say it's infinity either. I guess as I've drawn this wouldn't have a local min either, because there would be no point corresponding to what seems to be the lowest point in my drawing. Can I clarify anything about that? It's a lot of pretty advanced concepts, and proving all this stuff is pretty hard, but if you think about using mathematical like this, I think it is helpful. All right, the last 15 minutes of class, we're going to focus on optimizing over a different domain. So I'm calling this domain D2. It is still a closed and bounded domain. I should mention, I mentioned this in the other class, and I think you should know this, that closed and bounded domains is equivalent to another concept. We're effectively going to take this as a definition, although in some higher math you don't take it as a definition, you take it as a theorem you have to prove based on a different definition for what it means for a set to be compact. So whenever I use the word compact, essentially I'm taking that as a definition to mean closed and bounded. One word that in this context means closed and bounded, and that is a standard word to use. And this extreme value theorem generalizes to higher dimensions that are where you have compact sets. And we'll talk about that actually on Friday. We'll do an example of a function of 3 variables over a closed and bounded domain in 3-dimensional space. And that could be called a compact domain as well. Before I go on, I'll also say that sometimes math professors, when they use the word domain, they actually don't mean closed domain. By default, they mean domains to be open, to not contain any of their boundary points. But that's not the case here. I'm taking the domain just to be, what inputs are allowed, and whether it's open or closed or neither is up to you. Here's a different domain. Still thinking about rectangular coordinates here. The assumption is this is representing a point in the plane with rectangular coordinates. The sum of all points x, y, whose rectangular coordinates satisfy this inequality, what's that going to be? What kind of shape will that be?
Circle.
It's a circle, and the inside of the circle, technically speaking, the circle is the boundary. Just like over here, technically speaking, the square is the boundary, not the boundary on the inside. That's going to be a disk of radius 5 is the more official name for it. The circle is the boundary, with intercepts still at plus or minus 5. But because of the inequality there, I also include the points in the interior. If I just had a strict less than there, this set would only include those points and not the circle on the boundary. But because it's a less than or equal to, we are including the circle on the boundary as part of the set. Therefore, this is a closed and bounded domain. It is compact. And therefore, the theorem, the extreme value theorem, applies. You can use it to say, same function here, that this function definitely has a global max and global min value along this domain. They're not necessarily the same global max and min as they were on the first domain. Probably not. Are they still going to occur along the boundary? I think they still will here. But that isn't something you can just cavalierly say. You have to check it. To make a graph of the contour map over this domain, what you need to do is use an option in contour plot that helps you restrict the domain. And I typically tend to forget what this command does or what the syntax is. But I always remember in the documentation center that if I look up plot 3D, I always happen to remember that if I do that, I can find the commands that I'm after that are going to restrict the domain for me. There's an example here, about the third example down, right here. You can see it says you're restricting the domain there. Restrict the domain with region function, arrow function, then the point, then the inequality. That code restricts the domain. In this three-dimensional example, it restricts the domains of these functions when they're graphed in three-dimensional space to being a disk of radius 2 centered at the origin. I can copy and paste this code into the contour plot, although I do need to make a couple modifications. For one thing, I don't have any z's in the contour plot, so I should get rid of this z here. And for another thing, my disk is different. It's radius 5 instead of 2, so this should be a 25. There we go. We have restricted the domain of the contour plot to being this disk of radius 5 centered at the origin. And if you look at it, it does appear that probably the global max, well, for sure, is not occurring at these 4 points, but over here somewhere. You see this last level curve over here, perhaps right about there is where the global max will occur. And by symmetry, it seems that the global min might occur way over there, at perhaps a point that's across the origin as a reflection from the original point. I'm not positive about that, but that seems like it might be the case. How could we figure out what those global maxes and mins are? Well, I'm going to show you 2 ways to do it. One is we can create a function that is going to match this function along the boundary, a function of one variable. It makes sense to perhaps use the angle theta, the angular variable, as my one variable, as my parameter, so to speak. Parameterize the circle here. Plug that parameterization into the function f as a function of theta and see what kind of function you get. Graph it, that kind of stuff. So let's see if we can do that. How would we do that? I could give this function a new name, maybe call it g of theta. I want to be on the circle of radius 5, so I need to replace x with 5 cos theta and y with 5 sine theta. We're using polar coordinates, effectively. What's the formula for g of theta? It's probably pretty complicated. Since f involved powers of x and y, g is going to involve powers of cosine and sine of this new variable theta. So its formula is fairly complicated. Do we want to differentiate this? Find the critical points? Sounds difficult. It is actually doable, though I'm not going to do it by hand. We can find g prime of theta, for example, like this. We can solve for where g prime of theta is 0. Mathematica does produce some output for this using something called the conditional expression. Effectively, this conditional expression, along with this statement, says the answers look like this when this C1 is an integer available. It's not so surprising, it's a periodic function. NSolve can approximate those, but I think I'm just going to use plot and then find root. We only need to plot this over the interval. We only need to plot this over the interval from 0 to 2 pi. That's going to go around the circle completely. There we go. So this is what the function is behaving like along the circle of radius 5 as theta goes from 0 to 2 pi. Looks like a global max is going to be in the ballpark of 325 to 330. Occur when x is a little, or theta is a little bit bigger than 0, and a global min of around 170 or so will occur when x is a little bit bigger than pi. Theta is a little bit bigger than pi, which you would have to convert back to rectangular coordinates to determine which x and y that corresponds to. Let's use find root to find those. Find root where g prime of theta equals 0. You have to give find root a guess. Oh, if I guess 0, then I should get that answer that's a little bit bigger than 0. 197 as an angle that would be in radians. And to figure out where the minimum is, guess pi, and you do get an answer a little bit bigger than pi. So approximately, the global max value on this disk, or excuse me, on the circle, is about 326.485, and the global min, 170 something, yep, 173.515. And those will be the global max and min over the entire disk as well, because the theorem says that either occur at the critical points in the interior or along the boundary. Bigger and smaller than what happens at the critical points. That's got to be the approximate global max, and this has got to be the approximate global min. What x, y points do they occur at? Well, just find 5 times cosine of 0.197396 and 5 times sine of 0.197396. That point, where the global max is, and we can plug this into the original f as well to get the same output. 326.485. And then for the global min, probably 3.38899 is 2 pi, is pi plus 0.197396. It's probably symmetric here. So we should get the opposite of the first point. Oops, didn't need to do it there. Yep, opposite coordinates. And now plug that into the function. To get that min value 173.515. There's another way to find these, and I'm almost out of time, so I just have to give you an overview of this. This is what your completion assignment is about, and I know we're doing these completion assignments before we get to them in class. And that's called the method of Lagrange multipliers. And here's the idea of Lagrange multipliers. Pen, here we go. Pretend this pen is a vector. And what I want it to be is I want it to represent the gradient vector of the function f at various locations. For example, right here, pointing about that direction. One space right there. I want to think about this vector along the boundary of this domain. For example, right there, it's pointing in about that direction. As I move along the boundary, it seems to be rotating a little bit in the clockwise direction, perhaps. The question is, what happens when I reach that location of the global max? Well, it seems like it's probably perpendicular to the circle, normal to it, orthogonal to it. Same thing at the global min. Over here, the gradient vector points into this disk. It's got to point from dark to light. And when you're at the global min, it seems like it's going to be perpendicular to the circle. That geometric observation that probably is what occurs at global maxes and mins along a smooth boundary like this is motivation for the method of Lagrange multipliers. What you do is you create a new function. First of all, I can call it g. This is not the same g as before, whose zero set represents the boundary, in this case the circle of radius 5. That function right there, x squared plus y squared minus 25, would be a function whose zero set, when it equals 0, is going to represent the circle of radius 5 centered at the origin. You actually don't have to do the zero set. I could have gotten rid of the minus 25 here and put a 25 there. It's a little bit more traditional to think of it as a zero set. So I'll keep the minus 25 there and keep the zero set, the 0 right there. Again, the circle of radius 5 centered at the origin is going to be the solution of this equation. Solutions. You want that equation to be satisfied for points you're after. You also want, again, the gradient vector to be perpendicular to the circle. How can you guarantee that? Well, the gradient of g, we know, is going to be perpendicular to its level curves, normal to them, orthogonal to them. And what are the level curves of g? They're all circles centered at the origin. And in particular, this one is radius 5. The gradient of g is 2x comma 2y. What we're after is values, points along the circle where this gradient vector is parallel to, perhaps in the opposite direction, is the gradient of f. What was the gradient of f? Let's grad f. It's that. X squared plus y squared minus 10, comma 3 plus 2xy. What would it mean for these two vectors to be parallel? Well, possibly in the opposite direction from each other. It would mean that one is a scalar multiple of the other. The gradient of f is some scalar times the gradient of g. It's traditional to call a scalar lambda, which looks like that. And effectively, it's these two equations, this one and this one, that you have to solve. Actually, this is going to represent two equations, and this will be a third. You've got to solve this system of 3 equations and 3 unknowns in x, y, and lambda to help you figure out where these two vectors are parallel, and therefore where the possible locations of the maxes and mins are. The algebra for this gets kind of messy. Give me about 1 minute here to just describe it briefly. What system of equations are we going to get here? The first component of f, of the gradient of f, is 3x squared plus y squared minus 10. That has to equal lambda times the first component of the gradient of g. So that's one equation. The other equation is going to be 3 plus 2xy equals lambda times 2y. And the third equation is going to be this one. X squared plus y squared minus 25 equals 0, or if you prefer, x squared plus y squared equals 25. That's a system of 3 nonlinear equations and 3 unknowns, and theoretically it can be very difficult to solve. Is it solvable in this case? Well, the typical method is to solve these equations first for lambda. Like this and like this. And then set those two things equal to each other as long as you're avoiding places where you'd be dividing by 0. and try to solve that equation for x in terms of y along with using this thing too. How difficult is that? It's going to be pretty difficult in this example. Okay, you'd want to cross multiply, set these two things equal to each other. Here's a curved equal sign. Cross multiply, you'd get a cubic and y for sure. It'd be pretty nasty to do by hand. In your completion assignment, they are doable by hand unless said otherwise. Okay, but they can be pretty nasty, and that's the main thing you might have difficulty with on this next completion assignment. But that's the big idea. See you on Friday.